Good morning again, guys. Let's get back to our chemical equilibrium lecture. We're going to talk about the form of K now. So that's what we're going to be dealing with. I'm going to go ahead and share my screen again. Let's get right back into our lecture. So now that we know what an equilibrium constant looks like, K, and K has concentration of the products over the concentration of reactants. So that's what we're dealing with. And this is just a reminder of that the rate of the forward and reverse reactions are equal. We'll get back to that when we talk about kinetics. So what can we learn from an equilibrium constant? So I know that it's a ratio of products to reactants, right? If Kc is really big, really, really large, then the products are way more predominant than the reactants. So that means that reaction, as we've written it, if we were to write an AA plus a BB going to C plus D, just a generic equilibrium. If that K I'm assuming that these are all either gases or aqueous. If that K is very, very large, then D and C are very large compared to A and B. So that means that this reaction favors that direction. We get products. Strong acid, HCl, that's the kind of thing that we're dealing with here. All right. Now, if in the extreme, like HCl, when there is no HCl left, that B doesn't exist, or the A doesn't exist, there's nothing left of that reactant, then my K is undefined. Okay, and that's why you'll never see a K value for a strong acid. If there's no K value, it's a strong acid. All right. Now, if K is approximately 1, right, so this is our situation when Kc is greater than 1. If Kc is approximately 1, then that means we have roughly the same concentration of products as reactants. So we have a situation where neither one is particularly favored. We can talk about the reaction of H2O going to H plus OH minus. This happens in solution all the time. It's a spontaneous reaction. This should have been introduced when you talked about acids in 110. This is called the autoionization of water. This happens all the time. And we know that these concentrations are fairly fixed. Okay. So we know that there is no predominant species. All right. The other thing that we can talk about, Kc being less than 1, then I know that that product doesn't have a lot to it. It's mostly reactant. And so when we talk about that, we typically talk about this in terms of acids and bases because it's usually the easiest way to consider strong versus weak. When we talk about weak acids, they usually exist mostly in the one where the acid is still put together. So a generic acid comes apart to give me an H plus and an A minus, and that A stands for anion. That's why we use the A. Okay, and it's just a generic anion because all acids work in the same way. So it doesn't matter what that A is. It's just we took the proton off of it. And now we have concerns. All right. A weak acid is mostly going to exist as a HA. So we say that is reactant favored. Okay. Forward reaction is not favored. Reverse reaction is favored. Okay. So that's why you can see those values of K. Once you have a value, that will tell you roughly how much product to reactant there is. So again, if it's greater than 1, we have more product than reactant. If it's equal to 1, they're roughly equal. And of course, if it's less than 1, then we have more reactant than product. Okay, so that's what that means. Awesome. So let's practice with writing some K expressions. That's really what this is about. And we're going to be doing that using some values that we have. So I'm going to go ahead and scroll up a little bit. Actually, I'm going to scroll down a little bit. It says that I have 2 NH3. It's supposed to be an NH3 gas going to N2 gas plus 3H2 gas. And I know from my previous discussions that that's going to be a K equal to those products. So the concentration of H2 times the concentration of N2. That H is raised to the third power over the NH3 raised to the second power. Now, I know this may seem a little weird, but the way that I always do this when I have these written down, I know that my products are going to start all the way to the right, and I keep going writing product until I hit the arrow. And then I go back and do the stoichiometry on the products, and then worry about what's the reactant and its stoichiometry. Okay, so anything that's on the other side, the left side of the arrow. I know that seems a little weird to most people. They'd rather have it in the same order that it appears in the equation. It really doesn't matter which order it's in, so that's how I manage that. And that's why they always look weird. Okay, so I know that that's my Kc, the form of the Kc. Now they tell me that the concentration of N2 is equal to 3.0 times 10 to the minus 2 molar. When we do Ks, they should all be molar concentrations. All right. H2 is equal to 3.7 times 10 to the minus 2 molar. And then NH3 is equal to 1.6 times 10 to the minus 7. And I want to know what's that value of K. Okay, so I'm going to take those numbers and I'm going to plug them into the K that I've written. So annoying. So I'm going to take my H2 concentration, which is 3.7 times 10 to the minus 2. That's raised to the third power. That N2, the 3.0 times 10 to the minus 2, is raised to the first power. And that's over the NH3, which is 1.6 times 10 to the minus 7th. And that is squared. So that's the math that I'm going to have to do to get a value for this K. Handy dandy calculator. Now, I don't have one that I can show you on screen, but I'm using TI. Okay. One thing I will mention, if you don't know this, when you do times 10 to the whatever, you have to do this, and I wish I could show you that, but I can't. Second EE, that's how you have to do that. So when I enter the 3.1 second EE negative 2, and then I can cube that, which is that little hat. It's right below the clear key. Then I can multiply that by 3.0 to negative 2. And I divide that whole thing by 1.6 times 10 to the negative 7th, and that is squared. And I get 3.5 times 10 to the 7th. That is not right. Give me 2 seconds. Sorry. I apologize. My calculator and I don't necessarily get along. When I'm on a test, I will do these calculations like 7 times to make sure that I got them right. But I'm extremely comfortable with Excel, so I'm going to do this in here. 3.7 e to the negative 2. This is 3.0 e to the negative 2. I hope those values are right. I need to verify that. 1.6 e negative 7. So that raises that number to the third power. That's equal to that. That's equal to that number, second power, so squared. And then I'm going to take that, and I'm going to divide that by that. And 5.94 times 10 to the 7th. Okay, I was right. Awesome. I love it when I do stuff and it works. Well, it's not exactly the same, but it is the same order of magnitude. And so that gives me a K equal to 5.9 times 10 to the negative 7th. Now at 500 degrees, that's reasonable. Now, I look at that and I say, okay, that's not what I would see in a tabulated table, and that's because we typically don't look at it for that temperature. All right, but remember, they are temperature dependent. So that's how we do that calculation. Okay, questions about calculation that I did? All I did was plug those numbers in, raise them to the appropriate powers, and then do the math. I know it's going to bug me, so sorry. Okay, so our next question talks about this generic A gas plus 2B gas going to 3C gas. 9.22 moles of A, 10.11 moles of B, and 27.83 moles of C are mixed in a 1 liter container. Awesome. That can give me a molarity because I've got moles per liter. Yes. The reaction comes to equilibrium, and the concentration of B is 18.32 moles. Again, it's a 1 liter container, so that's the molarity of that. The concentration of A is 13.32 moles. And the concentration of C is 15.51. Then what is the value of Kc? So I have an initial condition, stuff that they gave me that was the beginning, which I don't really need right now. Okay, that information's there, but I don't need it. What I need is the information about the equilibrium, because that tells me what those concentrations are at equilibrium, and that's what I put into K to be able to find out what that value for K is. Now K in this case is going to be concentration of C cubed over the concentration of A times the concentration of B squared. So that's what I should be looking at. And again, since it's a 1 liter container, all of these are my molarities. Make sure that you do, when you do this, they are molarities. We have our C is 15.51, and that's cubed. We're going to divide that by 13.32 times 18.32 squared. Okay. Now, the other thing I want to point out to you is when I'm doing this, the stuff that I got initially, I put above the equation. I have the equation written out, I write the initial stuff above it, and the equilibrium stuff below it. When I do problem solving, this is something that I'm consistent with just because it makes my life easier. So that's the math that I need to do for that. And I get 15.51 cubed divided by 13.32 times 18.32, which is squared. And I get 0.8 835 times 10 to the minus 1. Yeah, I already took care of the 10 to the minus 1 by putting it as a 0.83. So my calculator says 8.35 times 10 to the minus 1. I already took care of that. Sorry. A couple of things that I want to point out at this point. We do not report units on Ks because it depends on the form of the K expression, what those units are going to be. And we really don't care what those units are as long as we've set that up correctly. So we don't usually report the units for that. It's just not reported. What was I going to say? Oh, you may have noticed that I was writing all the C's that go with this. There are lots of different types of K. We'll talk about some of the other ones in a little bit. So it's important, if we know what kind of K it is, to try and include that. All right. And like I said, we'll talk about different types of Ks as we move forward. So that will make more sense to you at that point. But that's why I went back and relabeled those because they can be different. So that's why I did that. And now I want you to try and work out these two on your own. So the two below, I have a reaction 3A goes to 5B plus 2C. You get concentrations for those. What's the value of K? And then 2NO goes to N2 plus O2. We have concentrations for those. What's the value of Kc for the reaction? So I want you to work those out. And while you're working that out, I'm going to fix this right here because it's going to bug me if I don't. And I apologize because it should have been fixed before you got it. But hey, at least it will be fixed the next time you use it. So I want you to go ahead and set those up, do those calculations. I will be back after I have worked them to I will be back to work them with you so that you can see what I did. Okay. All right, guys. So now that we're back, I have the reaction 3A. This is aqueous. Goes to 5B, which is aqueous, plus 2C, which is aqueous. At equilibrium, A equals 0.566 molar. And B is 0.598. I was going to put the M out in front so they'd all be molar, but I'm just going to include them with each of the numbers. And 0.239 for C. 239 for C. What's the value of K? So again, my Kc for this is going to be the concentration of C squared times the concentration of B to the fifth over the concentration of A cubed. I'm going to plug in my values. 0.239 squared times 0.598 to the fifth over 0.566 to the third. Okay. So that's the math I'm going to need to do to set that up. And I get 2.41 times 10 to the minus 2. And I don't know if I've mentioned this to you guys or not, so I'll go ahead and mention it at this point. At this point, I'm not overly concerned about how many sig figs are included. I try to be consistent with the information that was given to me. So in the first question, I had 3.0, 3.7, 1.6, so my answer was reported as 5.9. So 2 sig figs. In the second question, I had a number, the smallest of those had 3 digits, 9.22. And so the answer that I reported was 0.835. In this one, all of them are 3 digits, and that's why I put 2.41 times 10 to the minus 2. As far as your exams go, I will choose one question that will get graded 4 significant digits. The rest of them will not. You will get comments about it. Because if you're not reporting or not using all of the digits, you'll end up with rounding errors. And so I'll be able to see that that is what you did with your calculator. We should be using exactly what the calculator spits out to continue those calculations. So if we don't want to truncate anything, even though you may truncate it on your paper, don't truncate it in your calculator. Okay, so there's that. Now, the last question that we have for this says 2NO, and that's a gas, goes to N2 gas plus O2 gas. I have an NO concentration of 1.15 molar, an N2 concentration of 0.058, and an O2 concentration of 0.058. What's the value of K? And my value of K is going to be equal to the concentration of O2 times the concentration of N2 divided by the concentration of NO squared. I'm going to plug my values in, 0.058. Since both O2 and N2 are 0.058, I'm going to square that. It has nothing to do with stoichiometry. It has to do with the fact that both of those numbers are the same. And then I'm going to divide that by the 1.15, which is also squared because of the stoichiometry. I'll do my happy math on that, 0.058. And again, I get a 2.54. And it actually should only be 2 sig figs because the 0 in front of the 0.58 is not significant. So that should be 2.5 times 10 to the minus 3. Okay. Now I do get students who ask me, why do you do your calculations while we're watching you? I do that because I need to understand that not all of us are perfect with our calculators. And it happens that we don't get the right numbers put in, or we make a mistake while we're entering in, we get a weird value. And there are a couple of things about that. One, you should be able to look at that number and go, wait, whoa, that doesn't feel right. And you've seen me do that a couple of times. So I go back and verify the math. It doesn't feel right. The other thing is that it happens. I need you to understand that it happens to me. And I've been doing this since, 1991. So it's been a minute. It's okay that it happens. I'm not concerned that you got the right answer. I'm concerned that you got the right setup for that answer. And that's why work is so important when I'm grading your exams. So make sure that you're turning in your work so that I can see what you did. I do mean it when I say that if there's no work, then you get no credit. So if, as an online student, you turn in your test and do not give me any paperwork, you will get no grade. I am not kidding. Okay? Please don't push me on that because I need to see what you did. It's not just a question of I can't give you partial credit. I need to see what you did because it's more important that you understand what you were supposed to do than you got the right number. So those right numbers, not important, not at all. And so I need to see that work. That should be turned into the assignments to go with that test. And you should get it within 24 hours. Okay? All right. So that's that one. Now, I think, we are up to a questions, comments, problems type area. So if you have questions, comments, problems, concerns, let me know. I'm going to stop this video and set up the next one so that we can talk about the rest of at least another part of this topic. Okay. All right, guys, I'll talk to you later.